o'clock. Let's go ahead and get started. So we're going to finish up our lecture today, our whole chapter on MoM method and integral equations. And by the end of the homework that you guys are going to do, you'll be experts in this area, which is pretty cool. Or at least be able to pick up papers and read it and become experts, right? So you'll understand these derivations, these basis functions, and to write your own code for 3D scattering as part of a homework in a course is a pretty cool accomplishment. So like I said before, if you're able to do the plate, right, write the code to do the plate, then you can use any STLs. So you can start to do, electromagnetic responses or scattering from arbitrarily shaped objects, things, anything you can get an STL of. And you can make STLs by going into like a CST or a CAD modeling tool, drawing whatever you want, and then exporting the mesh as an STL. So then you can start to, solve electromagnetic scattering problems of any shaped objects, which you can't do using the approaches that we learned previously, which were mode matching and expansion in terms of cylindrical or spherical wave functions and applying boundary conditions to find the unknown coefficients to the expansions. So that's one thing. And then once you're able to incorporate impedance sheets that are arbitrarily shaped and you can learn how to design these impedance sheets, then you can start to cause anomalous scattering and you can design your scattered fields from arbitrarily shaped objects. So if I illuminate some object of any shape and I can design an impedance sheet to give me a particular scatter field like you guys did in your last homework for the 2D problem, then I can make any shaped object scatter any field that I want. And then there's all kinds of cool things you can do. So this is this first step, right? You got to learn all this stuff. All right, so I started up with this equation again, or this slide, because here's the big picture, right? What we're trying to do. So we have a object, a two-dimensional object, which is described by a triangulated mesh, or sorry, a tessellation in terms of triangular facets that describe a triangular mesh. And we want to be able to define basis functions on these triangular meshes. So we needed to learn how to integrate over triangular domains, and we need to learn how to describe currents over or through edges that are supported by two triangles, right? So that's the approach that we took. And here we see that there are two such edges. There's edge M, where the index M denotes the observation or the testing function. And there's edge N, which denotes the source or the basis function. So the way that you would interpret this physically is that there's current flowing all through here on this whole source triangle. So there's current on both these triangles. That current radiates. We calculate the radiated electric field due to the current that's supported by both these triangles through the use of the Green's functions, right? And then we observe that electric field over these two triangles, and we take the functional inner product with that electric field scattered or radiated by this current as observed with this basis function or this testing function and integrate, right? Okay. We derived this integral equation, which has a couple of parts here. We have the voltage vector Vm, which is found by taking the dot product of the testing function with the incident electric field and integrating over the domain of the testing function, right? What is the domain of the testing function? The two triangles. So this integral here, whenever it has Fm vector as the limit, that really means that there are two integrations to do. Two integrations over triangular domains. So this Fm will break into two integrals, one over Tm minus and the other over Tm plus, and you add them together. All right? Okay. And then we have our current coefficient vectors, which we will solve for. These are complex numbers. And then we have the impedance matrix. And the impedance matrix has two components or two parts. Here we have linearly varying component, which describes current. This is sometimes called the vector potential part of it, right? If you construct this integral equation, the same one, the EFIE, using a mixed potential approach, then you'll recognize that this comes from the vector potential terms, magnetic vector potential. All right, then you have this other component here, which you'll note is it doesn't vary linearly, right? because of the basis functions, what were unique about these basis functions? When we moved these derivative operators onto the testing and the basis functions, we had to ensure that our basis function, our testing functions, were differentiable, right? So they need at least a first order derivative. And they do. What is the first function that you can have that has a first order derivative? If you're increasing the complexity or the order of the functions. Linear, right? So it can't be constant. So you can't use pulses, right? Remember, pulse basis functions are constant approximations, piecewise homogeneous. So that means, or piecewise constant. So that means you couldn't move these derivatives onto the basis and testing functions because you can't differentiate them. And in a sense you can, because you would end up with two delta functions that are pointed in opposite directions that are the derivative of a rectangle function, technically. But then you have to deal with those, right? So the next order, higher order function is a linear function. So you can differentiate linear functions, and that's why these are triangle basis functions. In the sense, not only in the sense of their domains being triangular, but their amplitudes being triangular. So this is a triangular domain and another triangular domain, but the basis function itself varies linearly. Linearly meaning a linear function from the free vertex to the shared edge, and then it varies linearly but in a negative way, sloping down from the shared edge to the free vertex. So that's why they're triangular basis functions, because we can differentiate them. There are higher order basis functions that you can use, right? But these are the most commonly used, I guess. All right, so this term, since we take the divergence of a linear function, we end up with a scalar, yeah? So these two are scalar numbers, and that's a scalar number. So this is nothing but a scalar number. It doesn't vary linearly, right? And furthermore, what does the Fn represent again? What do we use Fn for? What do we use these Fn's for? When do they appear? For the currents, right? We expand the current density in terms of them. So you can think of Fn as J, right? Because J is equal to the summation of alpha n times Fn, right? So we're taking the divergence of Fn, meaning we're taking the divergence of J. So what does this quantity represent? Charge. So it's a scalar potential, electric scalar potential. So this is like a magnetic vector potential. This is the electric scalar potential. That's where these terms arise from, right? Or can be interpreted as. All right, so, and then we have the integration over both these domains, which mean there are four. This particular expression here with Fm and Fn, these two, each one of those integrals represents, it breaks into two integrals over triangular domains, right? So there are four triangles. This term here, these two integrals break into four triangular integrals, right? And those four integrals we saw were these ones. So there are four combinations of these. There's the minus, the plus, the minus the plus, and the plus, right? And your impedance matrix element, which was over here, which was just simply this expression, right? This is the whole impedance matrix element. Well, once you really consider what it means to integrate over these testing and basis functions, that one expression becomes these four, and then your impedance matrix then is, in the element, is then the summation of those four terms, all right? And be cognizant about those divergence terms. So remember, here we have divergence of that, and these basis functions have this kind of amplitude, right? So if you're in a plus triangle, or minus triangle is the left side of the edge, right? If you're in a minus triangle, then this divergence is the derivative of this function is a slope, positive slope. So the divergence will be positive. But if you're in the plus side of the edge, then this slope is negative. So every time you're on the plus side, you pick up a negative sign for this term and this term, yeah? So if you go here, wow, what's going on here? That's minus because the here we're working with both the minus and the minus, right? So both the left sides give you a positive slope. but there was already a minus sign. So let me show you that. There's already a minus sign here, okay? So these two came out positive, and therefore, hold on one second. Okay, therefore this stays minus. Now, one of these is plus now, so that means one of the two became a minus, right? And I think this is this one is the source, right? So that means the divergence prime of Fn was negative, and therefore one negative sign, this becomes plus. Now this one is the negative one here, so we get another minus sign. Here, they're both negative, but two negatives make a positive, and then we have the negative sign left over, right? So just be cognizant of that. The reason why I bring that up and why I colored them red is because it seems like a trivial thing, right? But when I wrote my first code of this, I had that bug, and it took me a little while to find it. So then I was like, okay, that's kind of a big deal. It's an easy mistake to make. But I had minuses everywhere. And it wasn't obvious, you know, when you go through whenever you get to a bug in your code, you got to go back to your analytic derivations and check all those, right? So you're probably a pretty good programmer, but it's easy to make mistakes programming. But make sure your analytic formulas make sense. Then you have to go to your code and check one by one which formula, and then it becomes a big deal. You guys will probably run into that. You'll find out. Gaussian quadrature, use that, and then you're able to evaluate these integrations in terms of summations. And that's it, all right? And then, of course, we went through all the self-term stuff, but in the end, the self-term, I'm not going to reiterate it again for a third time, but self-terms are nothing but these two formulae, and I gave you some code to do that, right? We checked near-term, inner, these functions. So you should be able to reconstruct the functions that I wrote from the slide, the material in the slides. Then we looked at the excitation vector. I changed this to VM. Last time we had it as I, but I think I just meant like the result of an integral. Because sometimes if you have an integral, you can say this is called I. But I think that might cause confusion with the current coefficients. So here's some code. Okay, so what's wrong with this? So I fixed the other error here, which was we had sine theta, cosine phi, sine theta, sine phi. Yeah, so sine theta, sine phi. It should have been sine theta, sine phi. I fixed it. But here, I say the polarization here is just x, 1, 0, 0. And if you happen to scan, so here is, say, z, and here's, let's say, x. If you happen to come in obliquely in this plane, and you're polarized in the x direction like this says, then technically, you don't have just x, right? So it's incorrect, that vector. Just be cognizant of that. If you come in at an angle, then you should have an x component and a z component. So this is not good if you come in at an angle, which this kind of says you're doing. So be careful when you copy this code directly, right? What you should really do is, and you know exactly how to calculate the components of a unit strength electric field based on the incidence angle, right? We did that last semester, so you can update this vector. Just make sure you get that right. All right? Okay, good. All right. In the end, well, I gave you, okay, the problem I gave you in your homework is you're not going to have to worry about that because you're incident in the XZ plane, and I chose Y polarization. So there's only that component, and it's not a function of the incident angle. And you're plotting everything in the YZ plane. So in the end, this thing probably won't affect you anyway because we take the tangential component only, right? Because you're going to take the incident field, you take the dot product with the row vector, right? Or FM, and that is a tangential to the model vector. So the fact that this really has an X and a Z component, the Z component won't appear anyway because it'll kill it when you take the dot product with rho. Okay, that is if the plate's in the XY plane, like the problem you're solving. Forget what I said. It's a bad thing to say. It's just saying that it won't affect it, but you should really be thorough with your codes, all right? So this is definitely not defined correctly. All right. Okay, so then we looked at calculating the surface currents. You can solve the matrix equation, and then you can go back to your expansion function definition and reconstruct the current everywhere. And I gave you a way to do that based on calculating the summation of the currents going through the three edges of a given triangle. And for us, you see there all the vectors are there, but we're going to only have three vectors. The one from here to the center. Hold on, let me clean this up. So from this edge, it's going to be, let's see, this is a minus, so be this vector, and through this edge is that vector, and to this edge is that vector. It goes to the from the center. The row vector is always the length from the center to the free vertex, because you want to calculate the current at the center of the triangle, so you can color the whole triangle one color. So you only have one current in that triangle, right? Technically, the current varies linearly in that triangle, but it's just for visualization. All right, then you can do things like this, and then you can calculate the far field using this formula where you incorporate the unknown coefficients in the current. This is nothing but the radiation integral, right? And here's some code to do that. All right. Then we got to here, adding impedance sheets, all right? So this is the bianisotropic boundary condition here. And what this represents is a particular, you know how we derived boundary conditions in the last class, right? We said we wanted to account for the tangential discontinuity in the fields. In the case of H discontinuities, we define the current density J. And in case of the E discontinuities, we define the current density M. So because of the equality that links those two, the current densities to the discontinuities in the fields, if you have a discontinuity in tangential H, then there must be a surface current present. Conversely, if you have a surface current along a surface or an interface, then the magnetic field must be discontinuous, right? Okay, this is a similar boundary condition in the sense that it's defined at an interface. Along an interface, you can have electric and magnetic surface currents flowing, and these electric surface currents can be excited by what's called the tangential average electric field, or the tangential average magnetic field, through these two proportionality constant tensors, all right? Proportionality constant means that it defines the relative strength between a given electric field that drives a current and the resulting current, right? So what are these tangential electric fields that are averaged and all that? This E tangential average is, it's E1, let's say, plus E2 divided by 2. And these are considered tangential, right? So tangential E1, tangential E2. And the H average is equal to H1 plus H2 divided by 2. And H1 and H2 are two sides of an interface, right? E1, H1, E2, H2. All right. So this is a boundary condition that you use to design metasurfaces. It's very related to the impedance boundary condition. In fact, it can collapse to that. And it kind of bears resemblance to the constitutive relation J equal to sigma E, if you consider only electric impedance sheets. But that's a loose analogy because the constitutive relation J equal to sigma E is for a medium, right? Sigma is a medium, a parameter that describes a medium. These are interfaces, all right? Okay, good. So anyway, if we have an impedance sheet that supports only electric currents that are generated by only electric fields, only the Y is non-zero, right? Every other tensor is 0 because we only want to allow electric currents to exist, and they can only be driven by electric fields. The electric current should not be able to be driven by a magnetic field in this particular case, so chi has to be 0. And we don't want any magnetic current, so these both have to be 0, even though that there will be an electric and magnetic field present, right? Okay, in that case, then what is the boundary condition for magnetic current? So here we have K, right? K is equal to negative N1 crossed with E1 minus E2, right? Okay, if this has to be equal to 0, what do we know about the tangential electric fields? E1 and E2. So we're saying this impedance sheet that we're considering should not support magnetic current. So K has to be 0. But we know K is equal to negative N1 cross E1 minus E2 by definition of a magnetic surface current. Yes?
I'm like a little confused by the interchange of using the K and the M notation.
Yeah, so that's another notation. M is the same thing. Matter of fact, it should be M. But K is used in this context because when we're talking about metamaterials and metasurfaces, there are also notions of media and magnetization. So here it is right here. This is why, right? So J omega P, where P is the polarization density vector field for like a dielectric medium that's been polarized by an electric field, inducing dipole moments, and therefore there's a field contribution to those, and so forth. J omega P is equal to J surface, where P is PS, which is the surface polarization, all right? Which is exists at interface, a theoretical 2D interface, right? And then J omega M is the magnetization. So time varying magnetization current density, or time varying magnetization can lead to a magnetic surface current density. So that's why they use K to not confuse with M. But we've been using M for surface currents that are magnetic, so you can think of that. That's what Balance's book does. M is a magnetic surface current. And I think he uses some other letter for this, or a different font for this. It's like a curly M or something. All right. So, okay, so what do we know? We know that the magnetic current has to be zero. Magnetic surface current is zero, right? And this is the definition for the magnetic surface current, and it has to be zero. So what do we know about tangential E1 and E2? They have to be the same, right? That means that tangential electric field is continuous across the metasurface or the impedance sheet. And that means that it doesn't even see it, right? The tangential electric field goes right through it. It doesn't even know it's there. All right, but the tangential magnetic field sees it, right? It has to be discontinuous because it supports this tangential surface current density, electric surface current density, yeah? Okay, so knowing that, if we go back to E average, what is E average for an impedance sheet that does not support magnetic current density? These are tangential components, yes.
So if they are the same, so it would be the tangential component.
That's right. If they're the same, then the average is nothing but either of them. Yeah? So this is equal to E1, or it's equal to E2. Right? That's only in the case of an impedance sheet that does not support magnetic currents. All right, so now we can look at this boundary condition. J surface is equal to Y dotted with E average, right? That comes directly from our constitutive material parameter boundary condition. And this we now can say is just equal to E1. Oh, okay, sorry. Y dotted with E1. Or this is also equal to Y dotted with E2, right? Either one. They're the same. All right, so that's our boundary condition. J is equal to Y dotted with E total. Remember, these are total fields. These are all total fields. Total fields and averaged, all right? All right, good. So in the case of Y being a diagonal matrix, and it's easy to invert it because the inverse of a diagonal matrix is nothing but the matrix with 1 over the diagonal entries as its diagonal entries, right? So that means this formula applies. And we can rewrite the boundary condition like this, except now we should say E1 or E2, whatever you want to call it, is equal to Z dotted with J, or E total, basically, right, on the impedance sheet. It's the same on both sides of it. So this can be rewritten as E total equals to Z dotted with JS. All right, so this gives us a way to utilize this boundary condition in moment method solvers, because what are we doing in moment method solvers? What is the unknown that we're solving for? Current, right? And we'll assume we know the impedances. So this is that boundary condition now where we can either use the left-hand side and stipulate the total field. We know the incident field. We want to stipulate the scattered field. So we define what we want the scatter field to be, add it to the known incident field, and we have the total field. We can either use that on the left-hand side for the total field term, or that's a design problem, right? If we want to do analysis then we know the sheet impedance already, and we just want to calculate what the scatter fields are from a known impedance sheet, meaning we need to calculate the current density J. All right? So here is the matrix. And remember, since it's diagonal, the basically the crystal axes have to align with the geometry, right? There can be no cross coupling. Okay. So here's the impedance boundary condition. Let's just consider this as E total, right? So E total equal to Z dotted with J. And we expand. So we're going to start from this boundary condition, and we're going to massage it so that we can introduce it into our EFIE, right? Because the EFIE that we derived already is only for PEC. So what do? Let's take this equality and let's expand our current density in terms of our RWG basis functions, or in general vector basis functions. All right? The next thing we do is we substitute that current back into the boundary condition. So E total here is equal to, and we can factor out these summations from the dot product. And we have the following expression, right? Now let's test the equality using the testing functions. So we're going to take the dot product of both sides of this equality with Fm, and then we're going to integrate over the domain of Fm on both sides, right? And we can pull out the summation and the constants from the integration, and then we're left with this equality. So Fm dotted with E total is equal to the sum from n equal to 1 to n of alpha n into this particular computation here, which is the integration over Fm dotted with Z dotted with Fn. All right? Yes?
We are supposed to be there in the second, like, the second row. Right?
No. Yeah, that's a good point. Whoops. I think I also need to add the, the discussion on E1 equal to, since there's no magnetic current, E1 equal to E2, then we can get rid of this average on the left side. So I'll update this slide. Good catch though. Yeah, that should not be there. Okay. Great. So everybody got this so far? Very nice. So here's an equality here in the middle of it, right? We can either use the left-hand side, which we called before the W matrix. Remember? WM when we did the 2D problems. That's where we design, where we stipulate the total field and calculate a W matrix, and we throw it to the left-hand side of the matrix equation. Or, so here's the W matrix right here. Oh, sorry. Okay. Or we use the right-hand side, right, when we know the sheet impedances. We can then define matrices from these calculations, right? This calculation we're going to call the W matrix. Then we have our current coefficients, the I's, right? This is our WM matrix. And then here we're going to call this the Z sheet matrix. All right? So this whole thing becomes this matrix equation. So we just need to incorporate this into our EFIE. This, we need to incorporate in the EFIE, and this matrix representation into our matrix equation, representation of the EFIE, right? All right, so let's do that. So here's our EFIE, but upgraded, enhanced for incorporation of impedance sheets, right? And remember, we're talking about triangulated meshes of three-dimensional objects. Could be any shape, surface that you want. You get an STL of any object, and you can then write this EFIE and solve it on it, right? So we're talking about conformal impedance sheets here, and we're talking about being able to design the reflected field from any shaped object by designing an impedance sheet from that, right? So it's a pretty powerful approach, right? This is very, very cool. Okay, so what have we added here? Remember what we had before. Our EFIE before was only, it was these terms only, right? Except this one was moved to the other side. So it was that equals to this, right? Without the minus sign. But now we've added this part, which is what we just derived. How can we add that? What did we say was the boundary condition for the EFIE for PEC scattering objects? We said n hat crossed with E1 incident, or not E1, let's just say E incident. N crossed with E incident plus E scattered was equal to 0, because we were talking about PEC, right? So from there, we said that E incident tangential is equal to negative E scattered tangential, right? And then we made the EFIE from that boundary condition. Now we're making an EFIE from a different boundary condition. Our new boundary condition is the one we just derived here, right? Which is this one. And we ended up with this terms, all right? So our new boundary condition here is, the new boundary condition is E tangential total is equal to Z dotted with J surface, all right? And we went through on the last slide how to convert that to an integral equation and then into an integral equation in the terms of the unknown surface current density, and then from there into a matrix equation. But okay, so what is E total tangential? Well, that's also equal to E tangential incident plus E tangential scattered. Well, that's equal to Z dotted with JS, right? Okay, now the incident field, we know how to express the incident field, it's here. The scattered field, we express that one here. That didn't change from the previous EFIE, right? Incident scattered. What has changed is this summation is now not equal to 0 like it was here. It's equal to Z dotted with J. And we calculated what Z dotted with J is. It was this here, right? This is E total, or Z dotted with J, right? So now what we're showing is E incident. So basically, if you read this in terms of the field components, what we have here is this is E total. E total equals to E incident, right? Plus E scattered. And those terms are the ways to calculate those field quantities, right? Okay, good.
So, but the tangential, the tangential electric field is not 0 right now.
No. The tangential electric field is related to Z dot with J, right? So here we have E tangential total is equal to Z dotted with J surface, right? It's not 0.
Like for the magnetic current.
No magnetic current. This boundary condition here, the way we've derived it, we said that the impedance sheets do not support magnetic current, right? Anyway, if we did support magnetic current, we'd have to have an additional term for the scattered field, because this computation of the scattered field here, the I times ZMN, that's assuming that this is electric current only. If you have a magnetic current, then the Green's function is a little different. Then you'd have to derive another term here, which is the electric field radiated by a magnetic current. You have to include that as well. So this EFIE is for, it should probably say impedance sheets electric only, right? Electric impedance sheets, meaning no magnetic current. Okay. So now here is our EFIE now that includes, so there's two equalities here. Don't get confused. There's an equality here and an equality here, right? So there's an equality here and one here. Now, what this integral equation is you use this equality, so this term in conjunction with these terms, if you want to design, if you know your E total, stipulate your E total, right? And if you do that, then you end up calculating this W matrix, and you move the W matrix to the opposite side. So here you would have W is equal to V minus I times Z, right? So what you would do is you would move this. Okay, so the way that this is, you keep the Z times I on one side, and then you move the V to the other side, and the W is already on that side. All right? If you don't want to stipulate the total field, or if you know the sheet impedances already, so you're not designing them, you know them, then you use this equality. Then your matrix equation is I times Z is equal to V plus I times ZMN, which is this one. right? And the reason why I write here, phase 1, phase 2 is, direct solvent optimization. You can directly solve this one and get, everything's known here except for IN. You can solve this and get the INs, right? The currents. Here, you can put this into optimization loop and you can optimize over the Z sheets if you know some cost function you want. So call this an optimization phase. All right? Is it clear? Have you guys started your homework at all? All right, start it, because you're going to get bugs. All right. Do you have a question?
So the pH sheets is just adding some diagonal terms to each edge in the Z matrix.
Good observation. Yeah, but not exactly. It was that case in 2 dimensions, right? So here, yeah, if you have, what you're saying is this in 2D, what we had, this almost looks like exactly what we had for PEC, right? Except this additional impedance sheet impedance matrix that you add to the ZMN matrix, right? So in the 2-dimensional case, when we use pulses and all that, this was a diagonal matrix, perfectly diagonal, right? But now that we have triangles, we're talking about edges here. So say the nth edge here may not necessarily, and then there's another set of triangles over here, right? And this is the nth edge here. Now, it may not be that only when m is equal to n do you get a non-zero contribution from this calculation here, right? Because if they are the same edges, so say this center edge is the same as this center edge, so we're talking about this m and this n. If we're talking about this is m and this is n, right? Then it will go in the diagonal entry of the matrix. Because everywhere that this calculation down here, the Z sheet equals to the integration over fm dot over Z dot of fn, anytime this is non-zero, then it goes in this matrix, right? You'll get diagonal entries whenever m is exactly equal to n, right? But that's not the only time that this is non-zero, because it could be the case where you have a triangle like this. So here's the m edge, and then you have this one, right? And say that this one here is the n. So even though these are not on the diagonal, m is not equal to n there, you still get a non-zero contribution from here because these 2 triangles are still overlapping. All right. So yeah, you have to, there's a little caveat there.
The other Z, like, tensor thing is diagonal.
You mean this one?
Yeah.
Oh, yeah. That's diagonal just by the way we're setting up the problem. It doesn't have to be, right? If you directly start here, then you can make that full matrix. There are only 6 independent entries in that because it has to be reciprocal and it has to be passive, or it doesn't have to be passive, but there's...
If it is non-diagonal, so the material has to be anisotropic.
This is still anisotropic if zxx is not equal to zyy, not equal to zzz. The difference is that the geometry is aligned with the xy coordinate system. So you only get what this says is you only get an electric field in the x direction due to a current density in the x direction, right? Because the y current and the z current have zeros here. So if this one was non-zero, then you would get an x-directed electric field due to, say, a y-directed current density. And you need some kind of geometry that's rotated diagonal with respect to the coordinate system in order for that, where you're defining these components and these, x, what is x and y and z. You need some diagonal geometry, so it's like that, so that if you come in with an x-directed vertical electric field, then the current flows along a diagonal, and then that diagonal current will give you both an x and a y directed field, right? So you got to rotate things. All right. The reason why I started with this diagonal impedance matrix is because there's a step that's not shown here. Step 1 here is to solve this direct matrix equation by stipulating what the total electric field is, right? But then you have to solve for the sheet impedances after that, which you guys did in your 2D homework, right? The last homework. And that, in the last homework when it was a 2D problem, E tangential or E total, these are scalars now because it was one polarization, TE. We did TE, right? Yeah, TE. J surface, right? These are all Z-directed quantities. To find the sheet impedance, you just divided these scalars, right? Remember? Okay, so that was after you solved this matrix equation here. But the problem now is that you're solving this particular thing. E total tangential is equal to Z dotted with J, right? How do you, so this is a matrix equation. You can't just divide, right? So you have to, okay, so you could try, you don't know Z is what you're solving for. And this does not have a unique solution unless the matrix is diagonal, right? So you could do like maybe a linear squared fib, but it's not a unique solution because you know what the total field is. You stipulated that. You know it's X, Y, and Z components. It's a vector, right? So this looks like this. EX, EY, EZ. But then you have this thing which has 9 independent entries. Really, there are only 6 independent if it's reciprocal. So let me write that. 6 entries. Then you have JX, JY, and JZ, right? So how do you solve that? You only have 3 equations and 6 unknowns. But if you make this impedance matrix diagonal, then this always has a unique solution, right? So that's why I did that.
I have a question.
Sure.
Here, when we calculate ZS matrix, so we integrate over Fn dot Z dot Fn.
Yes.
Fn and Fn here are the same.
Yeah, but they're in different places, right? The mth edge is in a different place than the nth edge. And remember, only when, so this matrix will only be non-zero, the entries of this, the mnth entry of this matrix will only be non-zero if Fn has at least one triangle in the domain of Fm. It means they have to overlap at least one triangle or both triangles. If they have no overlapping triangles, then you're integrating over Fm's domain, but Fn is 0 there.
Our argument. So I thought they're in the same place. You know what I mean?
You
We're not-
mean,
we're
is
not
this the
talking
same
about
R?
talking about- It's just Z. I
Uh,
don't know the meaning actually of this integral.
Okay, so here, look at this.
I know that we're integrate over the testing function,
Yes,
but multiplying it by Fn, I know that comes from the current,
yes.
but I don't know the meaning of the.
So this part here, Z dotted with Fn, that's nothing but eta times J, right? That's our boundary condition. Total field is equal to eta times J. And then Fn just is testing that so we can make a matrix equation out of it. Oh, shoot. So think of this. So let's say this triangle here, this is Fm, right? If Fn is way over here, then if I'm integrating over this, remember, Fn is equal to 0 everywhere else. Whenever we defined these basis functions, let's go back and just make sure that's clear. So whenever we defined these basis functions, they were piecewise defined like this. They're defined for all R, everywhere. But they're 0 if you're outside of the 2 triangles that support the basis function. So it's 0 everywhere except for where the basis function is defined. So that means when we're doing this, this basis function Fn here is 0 here. So you're multiplying 0 by this testing function integrating, you're integrating 0. So only when this Fm and maybe this one here is Fn, did these 2 triangles overlap? So Fn is not 0 for that triangle. This one also breaks into 4 combinations, right? Even though you're integrating only over here, you have both the basis functions
Yeah,
there.
so I think they always overlap because we're not talking about like scattering. We don't look for.
Well, they won't always overlap. Here's an example of why, right? So look here.
Was isn't
or let's go here. So let's say this is the triangle. This is FM here, right? If that's FM, then let's say this is edge. Okay, let's go to the edges when we define the edges. Oh, here. Here's the edges, right? Yeah. So here's edge 1. Say that's FM, right? So M is equal to 1. Now, if we're doing calculating Z sheet 1 comma 6, so okay, this is FM. FM equals to 1 here for FM. Then Z 1 6 Z sheet 1 6. That's going to be the integration of these two triangles over that domain. But here's edge 6 over here. But this is Fn or F6. And F6 is only defined here. So it's going to be, when we're integrating over these two triangles, we're going to be multiplying by 0.
Yeah, so eventually you just have those that have overlap.
Exactly.
That means when it comes to calculating impedance, we don't care about like other triangles.
Yeah. No, that's a good, this is a local boundary condition, right? It doesn't care about what's going on, on other parts of the scatter away on the other side of it, right? This boundary condition here, this one, I guess. It's a local boundary condition. It's a local phenomenon. The relationship between the current density and the total field there is locally, the impedance locally, right? Point-wise. Good observation. Okay. All right, so now we understand the EFIE, yeah? Good. Gosh, this font got messed up. All right. Here's code to calculate this matrix, all right? I'm gonna just move on, but go through this. You're gonna have, oh no, I didn't give you impedance sheet. Already doing a 3D RWG code as a homework problem in these classes is pretty cool. So I'm not giving you impedance sheet, but the code is there, and I'm pretty sure the one I uploaded, it only looks like this when I do presentation mode in PowerPoint, but the PDFs I made, these are fine, so you can be able to read it there, all right? Okay.
So that's a very similar process to calculating the excitation vector.
Yes, it's very similar, except maybe I should fix this so you guys can see it. Hold on, let me do something real quick here. So if I discard all of that and we do this, I move this way over here. The problem is it changes the font size. And then this one, almost done here. Font. Let's move this. Editing a PowerPoint with my fingers. This is kind of, okay, maybe that'll work. Let me play this now. Okay, hopefully you can see it now. So what are we doing here? We got to calculate this matrix, yeah? So first thing we do is we loop over the edges, the M edges, right? Now I call this edges total sheet because we only want to loop over the edges that are on an impedance sheet. If you have a composite structure that has impedance sheets partially covering it, and there's ground plane, maybe piece of metal. We haven't introduced dielectrics, that's a whole nother beast with this, all right? But we loop over the edges that belong to the impedance sheet, M and N, because we have to calculate the testing function dotted with the basis function. So we need to loop over M and N, and we check whether there's any overlap between FM and FN, right? And the only way to do that is to take the two edges and see if either they're both plus, so you take M, edge M here, you take edge M here. Oh, man. You take FM and M and N, right? The M and N index, you pass it the triangle plus vectors. Is it the case that these two edges share triangles and that happens to be both plus triangles, right? If that's true, then you calculate your diagonal Z sheet matrix. Then you know this integral is not going to be non-zero. So you calculate your diagonal sheet impedance matrix from your known impedances. Then you have to do this integration. So you get the free vertices and you set up all your quadrature rules. And then this is the same as what we had before when we calculated impedance matrices. And then we say ZS matrix is equal to ZS matrix plus the sum of edge length M, edge length N, and then we divide by 4 times the area of the triangle, which is just the Gaussian quadrature applied to this integration over here. And we have, here is where it is. So here's the weights, W, right? Then we have rho M dotted with Z, dotted with rho N. And this is a diagonal matrix, all right? Okay, good. And then you do the same thing. So if they're not, if M and N, the edge M and edge N, don't share 2 plus triangles, maybe edge M and edge N share a plus triangle and a minus triangle. Maybe the basis function is a minus triangle and the observation testing function is a plus triangle. So then you do the same thing. Or they're both minus or plus, or they're both minus, right? You have to check all 4 cases. And it could be that there are multiple of these if statements that are true, right? In that case, you need to accumulate the results, meaning ZS sheet. For each if, I only add to the running total of that mth element. And then here I would do the same thing, right? Because it could be that multiple of those conditions are true. You need to sum them all up. All right. Total field vector, same thing as the incident field vector, except now this should probably say WM, right? And here we have E total, and we integrate against the testing function. Here's the code to do that. Calculation of triangle impedances. So here, now that we have a diagonal impedance matrix, we can calculate these impedances. So we solve by stipulating the total field, right? Then we need to calculate the impedances. Well, we know what the stipulated total field is. We just calculated the induced current density by solving this matrix equation. We can then find the Z's by going back to the boundary condition, which is E total. There's the Lth triangle. That's what this index L means. There are L total triangles. The Lth triangle, the impedance is Z, say L, dotted with J, L. So to solve this, this means element-wise division. So you take the element of matrix E, the vector E, the x component, and divide it by the x component of the current. The y component divided by the y component. It's called a Hadamard division. Or you can write it like that, right? Okay. So what are we doing? We're saying the entire triangle, the impedance associated with the triangle is constant for the whole triangle, and it's defined as E over J as calculated at the center, or evaluated at the center of the triangle. All right? Similar to the current. Okay. So there's an approximation used when I say this whole triangle has the same impedance. Why is that? Because we know the triangle's impedance is supposed to be E divided by J, but J varies linearly along in the triangle. So J is changing over the face of the triangle, so is E. E total changes over the whole triangle. So technically, the impedance should be a function of R as well. But we're saying, okay, ignore the variation of the current in the total electric field over the face of a triangle, or the domain of a triangle. Let's just say that it's the center, right? So it's an approximation. Just be cognizant. So here's an example problem that we solved using this. It's a sinusoidally shaped metasurface, and it's an electric impedance sheet. It's suspended in free space, and it's parameterized like this in the z direction as a function of x. It's 2 pi x over w times lambda over 2. So it's a sinusoid, right? So it's a normally incident plane wave. It's polarized in the x direction. We want to design the impedance sheet such that this conformal sinusoidally shaped metasurface scans the reflected beam to an angle of 20 degrees off broadside, which is the normal of this thing, in the z direction. So it'll scan it to 20 degrees. And the length along the x direction of this is 3 lambda, and along the y direction is just 1 lambda. And we're illuminating at 10 gigahertz. Just a super quick, easy thing, right? So here's the design. So you solve the EFIE that's been enhanced with impedance sheets, and you get this for the magnitude of surface current density in the phase that we plot on the impedance sheet. The impedance sheet, after you do the calculation of the impedances, you get this for the real part and the imaginary part. So it's a complex sheet, but you have to remove the need for the resistances using optimization. That's what I do, but you can solve that problem whatever way, right? And here's the far field pattern. We scan it to 30 degrees, right? Exactly what we wanted it. So this sinusoidally shaped metasurface illuminated with a normally incident plane wave in the x direction, E incident, right, scatters a collimated beam to a 30-degree angle.
Why it have to be sinusoid?
Doesn't. It could be anything. I just picked this as an example. It could be any shape, right? The Virginia Tech logo, for example. And then you can design that thing such that when you hit it with a plane wave, it scatters a scanned beam and collimates, or it could become a lens, or whatever you want it to be, right? That's what's cool about these. Or you can make, so what's really cool, what I like to do is, let's say you have, let me see. Say, doing this now, what you can do is something which is super cool. What's going on here? Say you start with the Virginia Tech logo. Okay, let's do it the other way. Say you start with a metasurface that's the Michigan logo, right? So this is an STL, and we write the EFIE for this STL. It's a three-dimensional object, and we illuminate it with a plane wave. And I designed the impedance sheet because I can stipulate whatever scattered field I want. It could be anything I desire, right? And illuminate it from any known incident field, and of any shape. In this case, it's the shape of the Michigan logo, and I have some incident field. I'm going to define the scattered field to be that would be scattered from the Virginia Tech logo. So then you hit this thing with a plane wave, and it scatters the VT scattering. It scatters like this one would under the same incident plane wave. And you can design a metasurface to do that because you have full control over the scatter field. The trick is to make this passive and lossless, all right? So that took a lot of work. We figured out how to do that, but it's not easy. Yeah.
Design like that is normally restricted to like one incidence angle.
Oh, for sure, yeah. Yeah, this thing obviously scatters differently as if you change the illumination, then the illusion's broken, right? Well, I did one where, and we got a little paper on it, where we made a metasurface shape like a cube scatter the exact meseries of a PEC sphere. So if you detected or measured the fields anywhere around it in space, you would only conclude that it was a spherical scatter, but really it was a cube. But that's like a toy example. And no, we didn't implement it, but it's passive and lossless, so you can with printed circuits. Problem was we needed to incorporate a way to, we needed to come up with a way to incorporate dielectric, and we've done that now. Some ongoing research in our lab now. Okay, so cool stuff, yeah? All right. All right, so that's the end of method of moments and integral equations for this course. All right, make sure you start your homework and you finish that, because that's going to be it's going to be a lot of work, right? Okay, well, let's move on to the next lecture. Next chapter even. So we're done with all of that. And now we're going to get into some even more fun stuff. I don't know how it could be any more fun than what we've already studied. But this is also a super cool topic because it's riddled with geometry. Differential geometry even better. So this is geometrical theory of diffraction, right? We're going to study all the way up to that. And in order for us to even be able to embark on this journey of learning how to solve Maxwell's equations in the guise of differential geometry and asymptotics, we need to be able to speak the language of differential geometry. We need to learn that. So we're going to do that first. We're going to study some of the basics of differential geometry. All right? So let's dig into it. So first thing we have in differential geometry for us, for geometrical theory of diffraction applications, we're going to be concerned with two types of objects. One is a space curve. It's a line. Where do lines arise from? The corners of things, like the corner of this screen here, or the corner of a table, or the edge of a PEC, or the rim of a reflector antenna. These are all sharp edges. They are defined by edges, right? And they're conformal. They have different shapes. They're curves. So we have to be able to describe the curves that are, edges or lines in space. They're called space curves. The other geometric entity that we're going to be concerned with are surfaces. So, and these surfaces are not planar. They're curved, and we need to be able to describe them and calculate their curvature and set up local coordinate systems and you know, the normals and parameterizations and all of that, all right? So let's start with curves. So a curve may be pictured as a trip taken by a point in motion, right? So here's some point, let's say. This point is in motion along some arbitrary path in three-dimensional space, all right? So we need to be able to describe the path, mathematically describe the path of any given particle, right? So any point in space can be described by a position vector. This is a key concept here. A position vector points to different points in space. It always has its tail at the origin, and it points to the XYZ coordinates of a point, right? Now, if we can parameterize this position vector R such that its tip traces out some path, then we have a way to describe a curve if we're able to describe this function, right, as a function of some parameter. So if at any time t, the position vector's components can be found by evaluating the functions x of t, y of t, z of t. So this is a vector, right? Say that the coefficients of that vector, or the components, these components depend on some other parameter t, right? Then this vector varies as a function of t, and the locus traced out by the tip of the position vector defines a space curve. So here, r as a function of a parameter t is equal to x of t, x hat plus y of t, y hat plus z of t, z hat. Or you can write it like this, x of t, y of z, and z of t. So this can be thought of as a mapping, right? So there's some interval here in a 1D space from, say, t naught to t, right? And we're mapping points on this interval over to x, y, z, some curve where each point on this curve is defined as r of t. So I pick a point on this curve, right? And through r of t, the mapping function, which has three components, right? It has x of t, x, y, and z components, but they're all functions of the same t. Then if I define a t, then I can define a vector in three-dimensional space and it points to some point. If I can design these functions, x of t, y of t, z of t, judiciously such that they trace out the curve that I want, then I have a parameterization for the curve, right, as a mapping. Yeah? Okay, good. All right, so what are some parameterizations using this framework for different curves? Here we have a straight line. A straight line is parameterized by this parameterization. R of t is equal to a plus bt. What is a? A points to the beginning of the curve, right? Or any point on the curve, I guess, because t could be minus infinity to plus infinity, so it will trace out the entire line. But some point on the curve a, right? Here's this vector a. Then we have a vector b, which is tangent to the curve, in the direction of the curve, right? So we need those two vectors, and then we can parameterize the entire line, because if I scale that tangent vector by t, then this vector b gets longer and longer, right? So maybe this is b now, t times b, right? Yeah? Now, if I add these two, then here's the r of t. You go from the tail, or when you add these two, it's a plus b times t, right? So as I vary t over some interval, it traces out the entire line. Everybody understand that? Very nice. The helix now, r of t, so this helix, this is the parameterization of a circle in the xy plane. You've probably seen this, a cosine t plus a sine t, a circle of radius a, right? But now I'm gonna add a z component to that parameterization. So as you're going around the xy plane, drawing out a circle, you start to lift linearly, constantly into the vertical direction. So it traces out a helix, right? So given a given t, you could think of this as theta here in this case. Well, t's better, right? But if it were theta, then it'd be very clear that this is a circle, and then you have some parameter lifting you up out of the xy plane, right? Conic sections in general. So how do we define conic sections? We have oh my gosh. We have a directrix here. This line here is called the directrix. Here's the, say, xz coordinate system, right? Xz coordinate system. I have some curve here, And the property of a conic section is that the distance between what's called the focus and the curve, a point P on the curve, is equal to, so that's PF, that length is equal to PL multiplied by E, right? Or, okay, so it's the other way around. So let me start here. A directrix is parallel to the x-axis. It's parallel to the x-axis, and it's some line, maybe somewhere behind this thing, right? The length of L to P is equal to the eccentricity parameter E multiplied by the length from P to F. F is called the focus, and the parallel line is called the directrix. So that's how you define these conic sections. Now, okay, so what do you guys know? You guys know the parabola, right? We know the property of a parabola is that every single one of these rays are the same length, right? If you go to some aperture, from focus to the aperture, they're all the same length. That means they're all going to have the same phase and the reflector collimates, right? So let's assume that this aperture plane is nothing but the directrix, right? And then you have your exact same thing so the parabola has eccentricity equal to 1. So that means the length from the focus to the reflector, or the length of the focus to the curve, parabola, is equal to the length of the ray from the parabola to some aperture. Call it the directrix here, but if you put this in front, then it's the aperture plane, right? So that's the same property. Because this ray here from, oh my goodness. This ray from the directrix, which is behind the parabola to the point P, well, let's say that now we define an aperture plane here, which is the same distance from here to here. So then this distance here is also PL, and just call this the aperture, right? Same thing. Okay, so in particular, a parabola, you can parameterize in the following ways, right? R of t, so we can have this parameterization in terms of R and t like we've been doing, right? Where F is defined as the focus along the z-axis, and t is the parameter. Or you can parameterize it with this parameterization in the xz plane. Or you can parameterize it with this radius vector. This is like a polar parameterization, where psi is the angle between the focus and the z-axis, like that, right? Okay, or an ellipse. Ellipse is r of t equal to a cosine t, 0 b sine of t, right? If the ellipse is in the xz plane. So it's the same as the circle, except now we have a and b are different instead of just a and a. Or this is the x Cartesian parameterization of it. Or this is the polar parameterization of it here. So there's a bunch of different parameterizations, right? Ellipse have two foci at plus or minus f, and f is given by this expression here. All right. And then there's a way to calculate the eccentricity of this as well if you need to. Then hyperbola is the other one, and the parameterization for hyperbola. So use these in like Gregorian and Cassegrain subreflectors for dual reflector systems that are paired with a main reflector that's made out of a parabola. So all these parameterizations are relevant, right? These conic sections. R of t, now they're hyperbolic functions because the hyperbola. And here's the Cartesian parameterization and the polar parameterization and where its foci are and so forth, right? Okay, good. Now, these all can be constructed by considering this geometry here where there's two cones, tip to tip, and they have their axis aligned. And if you intersect this two-cone system with a plane that is orthogonal to the axes of the cones, then you get a circle, right? Because you're just cutting the ellipse directly orthogonal to the axis of the cone. But if you rotate this, then you can get an ellipse because you'll cut it at an angle if you rotate the plane of intersection. If you use a vertical plane that's aligned with the axis of the cones, then you get hyperbole. And if you do one cone, but you intersect it at an angle, then you get a parabola. Yeah? Okay. let's look at the tangent vector and the arc length here. So these are other things that we need to define. So we have, for a curve r equal to r of t, now we know how to parameterize these curves, right? For a curve r equal to rt, its tangent vector at the point rt, wherever we're pointing to. So some point on this curve, wherever we're pointing to on this curve r of t, at that point, the tangent vector is the velocity vector, and that's calculated using the first derivative of the parameterization, or the position vector. How is that? So what is the derivative? What is the definition of a derivative? dr dt, right? Well, the derivative, if you write it out in terms of its definition, it's usually f of a, or f of x plus delta x minus f of x over h, right? And then you take the limit as h goes to 0. But here in the vector derivative sense, it's r of t plus delta t. So add a little bit to the parameter of the parameterization t. So this vector will move slightly ahead along the curve. And then you subtract r of t, where you're at, and you divide by delta t, and you take the limit as delta t goes to 0. Look what happens when you take this vector, r of t plus delta t, and you subtract from it r of t, then you get, so r of t is negated, then you get this vector here, right? And that vector there is tangent to the curve. So if you differentiate your parameterization, then you get a tangent vector along the curve. Tangent vectors are super useful because then I can start to integrate them and I can define arc length, right? I can integrate along the arc, because what do you need to integrate like a line integral along a particular path? You need dl along that path, right? We can get dl as the magnitude of this tangent vector, because that tangent vector is going to follow the curve, and I'll just take a differential displacement along the curve as a differential displacement in the direction of the tangent, and then I can integrate it. So tangent vector there, yeah? So this is, now all you have to do to calculate the tangent vector is differentiate your components of your r vector. So dx dt, dy dt, and dz dt. If we look back here for the ellipse, I think we'll do one of the examples. But derivative of this is a times negative a times sine, and then a times cosine, and b. Now you have a tangent vector everywhere, right? Okay. Good. All right. Okay. Now we want to calculate what the speed of the parameterization is, all right? It's called the speed of the curve, and that is nothing but the magnitude of your tangent vector, all right? So if this particle zipping along, because your parameterization is defined such that it really sweeps through the curve fast, then that tangent vector is going to be long, right? It'll be a super long tangent vector. But if you're trucking along the curve slowly due to the way you parameterize it, same curve, it's a different parameterization, then it could be, this tangent vector could be small, meaning it has small magnitude, right? And all you have to do is find the magnitude of your dr dt. All right, now special curves that we're going to first study, but we won't restrict ourselves to that, are curves which have unit speed, v of t equals to 1 for all t. All right, it's called a unit speed curve. Otherwise, the curve is called an arbitrary speed curve. All the geometry of what we're going to do with Fernet, Surret, frames, and all of that are way easier. The formulae are easier to evaluate for unit speed curves. But you can easily do that for arbitrary speed curves. So these are kind of hard to parameterize. You have to parameterize them such that you move along the curve at the same speed, constant speed, uniform speed equal to 1, unit speed. All right? So the distance traveled by a moving point is called the arc length along a curve, and the differential distance d sigma can be found as d sigma equal to v dt. Why? Because v here is the velocity, and I multiply, it's a function of t. If I take the velocity and multiply it by a differential time interval, then I get a differential displacement, right? This is from kinematics or whatever. So the arc length of a curve from a reference instant t naught to a variable instant t is like this. Sigma of t is equal to the integral of the magnitude of your tangent vector times dt. That comes directly from here. You integrate both sides. Yeah? So that's how you find the arc length of any curve. And as I was saying, this r of t is really a mapping from some interval on the line to some space curve here, right? And then you get a tangent vector here. So this vector is tangent. Yeah? Okay. So I think we can stop here. All right, any questions? Start your homework. Because you want to get that done early, because I'm gonna give you another homework the day that you turn that one in. Because we're gonna be behind. We're gonna get all into geometrical theory of diffraction, and you'll need to practice some of that, all right? All right, good. See you guys.